Okay, picking back up with some integration by parts. Picking off from our last video, we started looking at example 4, e to the x sine of x dx. Looks like we might want to reverse this product rule. The name of the game is integration by parts. We are using the LATE acronym to help us out with a u substitution. We're going to let u equal sine of x dx. There were no logs, nothing algebraic, something with trig. Du is the cosine of x dx. That means that dv would be what's remaining in the integrand, e to the x dx. Take an antiderivative, we have v is equal to just e to the x. Now, what we should look at right now is very plain and simply that this integral becomes sine of x times e to the x. And then we'd have the integral of, well, here's our v, we'll have e to the x, but our du is the cosine of x dx. Right now, this probably seems to be exactly like example 3. You'd probably say, okay, well, this is all well and good. Now we're just going to have to look at this integral. Sadly, we don't know an obvious antiderivative here. Students will correctly guess that we need to use integration by parts yet again a second time. And usually what kids will do is exactly what they did in the beginning. They'll say, let's let u equal something logarithmic. Well, we don't have that. Algebraic, we don't have that either. But we do have the cosine of x. We could very quickly let our dv then be e to the x dx, just like we did before. But I think you're going to see quickly that we're going to be in a bit of trouble pretty soon. Du is equal to the negative sine of x dx. And here we'd have v is equal to e to the x. So tell you what, for our beginning term here, sine x e to the x, I'll just bring that e to the x out in front. And then tell you what I'm going to do is treat this integral as another uv minus the integral of v du. And very quickly, I think you're going to see that we're going to have uv, well, that's the cosine of x e to the x. But this time, our integral isn't getting any better. In fact, what you're going to notice is we're in this kind of a vicious circle where we're back to another trig function times e to the x. And in fact, we can distribute that negative in there real quickly. And if I distribute this negative and bring the e to the x out in front, let's see, distribute a negative in here. By the way, once you distribute a negative, I think you could see that there are 3 negatives then. 1, 2, 3. 3 negatives would still multiply to just a negative. So, my goodness, all of a sudden, you look at where you are and you're right back to another integral of e to the x sine of x dx. If that looks familiar, it should, because that's what our original problem was. So all of a sudden, kids will say, well, should I do integration by parts again? I think very quickly kids will realize that would be foolish. We're in this deadlock. We're in this cycle where we keep bouncing back and forth. But take a look at this. This is kind of cool. The original problem was, in fact, e to the x sine of x dx in this integral. Tell you what, my goal is to solve for this. How about we add an integral of e to the x sine of x dx on this right side? Then, of course, we'd have to do the same thing on the left. And indeed, we can do that. We're just doing some basic algebra here. We'd get 2 integral of e to the x sine of x dx would equal e to the x sine of x minus e to the x cosine of x. Well, you might wonder if we're pretty close to wrapping up. Indeed, we are. We could say that this original problem, e to the x sine of x dx, I'm just going to divide by 2 on both sides and realize this is where we're probably going to have to remind ourselves that we would have had a final answer that would require a constant. We could just put a plus c there, and that's what we do. So that's how you can deal with this cycle of alternating between trig functions. Take a look at this next little bit of a definite integral of u dv. You might have noticed every single problem we've done so far has not had bounds on the integral. You might wonder, well, how on earth do we deal with that when we do see it? Would we still have a uv minus the integral of v du? Indeed we will, and this second integral will be from a to b, but then just applying the fundamental theorem here, we'd have from a to b as well. So that's how we can make a quick adjustment. Take a look at number 5 real quickly. The inverse tangent of x is the integrand. My goodness. We know a derivative for the inverse tangent of x, but we don't know an antiderivative of it. So this can be a puzzling question at first. Obviously, a u substitution won't help us. And we don't know an obvious antiderivative, so instead let's just use our late acronym and see if maybe somehow we can get some help. We don't have any logs, we don't have any algebra, but we do in fact have something trigonometric, or in this case an inverse trig function. And if we let u equal inverse tangent of x, dv, you might not be surprised, would just be dx. The derivative of inverse tangent, I hope you remember, is 1 over 1 plus x squared. We'd also need a dx. And then v would be, plain and simply, just an x. So let's go ahead and see if we can finish this problem up in light of what we just saw. We'd have uv, and we'd apply the fundamental theorem, evaluating that between 1 and 0, minus the integral of, an integral from 0 to 1 at that, v du. And we could say, well, what is our uv? Well, that would be inverse tangent of x times x, evaluating that between 1 and 0. Over here, we could say, well, we're going to go between 0 and 1. Our v is simply an x. Our du would be 1 over 1 plus x squared dx. And at first glance, this might not seem to have helped. You might even wonder, my goodness, has this been any help whatsoever? I hope we see that in the beginning at least. This looks more promising, that we can say that using that fundamental theorem, we'd say inverse tangent of 1 times 1 minus the inverse tangent of 0 times 0. And inverse tangent of 1, of course, is pi over 4. And inverse tangent of 0 is 0. So this whole beginning expression actually is just going to become pi over 4. We look at this v du in the integral, though, and this might be a little bit more thought-provoking. Here's where we need to realize that what you've done in the past still very well can come into play. We should, in fact, wonder if there's an obvious antiderivative here. We don't seem to see one. So you might try a u substitution. By the way, I'm going to write a w substitution. Let's let w equal 1 plus x squared. dw then would become 2x dx. Or another way of writing that is dx would be dw all over 2. And our bounds would change on this integral as well. If I let x equals 0 and plugged it in for this w, 1 plus 0 squared is just a 1. If I plugged in a 1, 1 squared is 1, 1 plus 1 is 2. So my new bounds would be from 1 to 2. I'm going to have 1 plus x squared down here is my w. My x, of course, is going to get canceled out. dx is dw all over 2x. Forgive me, I did not bring that x down earlier. You can see why we're checking this out here. The x's are going to cancel. And then nicely, very nicely, I think you can see we're going to have here's just pi over 4. But I'm going to bring out a 1/2. And then we can say we're going from 1 to 2 from 1 over w dw. At this point, let's just continue off to the side. The antiderivative of 1 over w is actually the natural log of the absolute value of w, but everything is positive on the inside, so I don't even need the absolute value around that. And at this point, we can very quickly just do some evaluating. We'll plug in with our fundamental theorem. This would be the natural log of 2 minus the natural log of 1. Natural log of 1 is 0. Final answer would be pi over 4 minus natural log of 2 over 2. No constant. Please realize there's no constant here when we have a definite integral. Well, what I'd like to leave you with, and we'll see how we're doing with time here, is a wonderful way to deal with integrals, a method known as tabular integration. It's really integration by parts, and it's a wonderful way that we can very quickly go ahead and apply integration by parts repeatedly. If you're really on your toes, example 6 is exactly the same problem as example 3. Example 3, we did integration by parts twice, x squared e to the x. So tabular integration is a way that you can more quickly go through integration by parts. What you generally will see is usually you'll have something algebraic out in front. And in fact, what we can do is start off with a column for u, and we'll say here's x squared. For our dv, you can say here's e to the x. And let's just go ahead and take derivatives. What's the derivative of x squared? Very quickly, you'd say that's 2x. What's the antiderivative of e to the x? Simply e to the x. What's the derivative of 2x? Well, it's just a 2. And the antiderivative of e to the x is simply e to the x. Let's keep going. What's the derivative of 2? Well, that's down to 0. And what's the antiderivative of e to the x? We'll have e to the x. What you're seeing is you stop once you get to 0. And we're going to draw these little diagonals here. And here's what you need to remember. It's going to alternate between plus, minus, back to plus again. And what we'll see then is we would have on this diagonal x squared e to the x minus 2x e to the x. Finally, plus 2 e to the x plus a constant. And this is a shortcut way to do integration by parts when you know that you have to do that repeatedly. Let's compare with our original answer. You can see right here we have exactly the same thing, but way more quickly. Again, you just need to alternate between a plus, a minus, and a plus. Let's try one more. Let's say that we have x cubed sine of x dx. We could have our u equaling x cubed, our dv equaling sine of x. Our derivative would be 3x squared. Antiderivative of sine would be negative cosine. Derivative of 3x squared would be 6x. Antiderivative of negative cosine would be negative sine of x. Derivative of 6x would be a 6. Antiderivative of negative sine of x, would be the positive cosine of x. The derivative of 6 is 0. Antiderivative of cosine is sine. Now, let's draw in our diagonals. Make this a plus. Next one would be minus, plus, finally, minus. Write it out. We'll have x cubed times negative cosine of x. We can just bring that negative out in front. Then a minus and a minus is actually going to make a plus in this next one. We'd have plus 3x squared sine of x.